Okay, so good morning, everybody. Welcome to the special lecture today. So we have Professor Zhouchen from Peking University. So Professor Lin received a PhD degree in applied mathematics from Peking University in the year 2000. He is currently a professor with the State Key Laboratory of General Artificial Intelligence, School of Intelligence Science and Technology, Peking University. So he is a new board member of ICML, and I'm looking forward to working with him. And he's also a fellow of the IAPL, IEEE, AAIA, and CSIG. So today he will be talking about advances on the training algorithm for large models. So we are very much looking forward to your talk. Okay, please start.
Thanks, Professor Sugiyama, for the invitation. I haven't seen Sugiyama for at least 6 years, I think. So it's very honored to visit the RIKEN again. Hope that I can have some collaborations in the future. Today I will talk about the training algorithms for large models. So I will talk about two recent work. The first is about training algorithm itself. Is to make the training faster. The second is to make the memory usage more economic. It will help you to reduce the memory consumption. We know that we have been in the large model era. Is considered as the second phase of deep learning. But before deep learning, the requirement on the computing power is really benign, right? The increment of the computing power is very slow. But after deep learning, the increment of the consumption of computing power increases very quickly. It's said that the computing power will double in maybe 14 months or something. Definitely faster than the Moore's law. So in the one hand, we have to make the training faster. On the other hand, we have to make the memory usage smaller. Both can constrain your training length. Say if the memory consumption is too large, you have to split the training into multiple clusters. So the communication parallel computing will constrain the speed of training. So the first algorithm focuses on how to make the training faster. We know that actually the existing training algorithms for deep learning and even large models actually comes from the classical optimization methods. But we have to do two tricks on the classical training algorithm. The first is here I give two examples, actually three examples. We know that ADGRAD and IM's Prof were popular maybe 10 years ago for training the deep neural networks. But actually, they came from the traditional gradient descent. How to modify the algorithm? They use two steps. The first is this is called the adaptive learning rate. In the traditional gradient descent, this learning rate is say is global for all the coordinates. This is the scalar. But for the methods for neural networks, this is component-wise dependent. Because this computation is component-wise computed. The square root and the division are both computed component-wise. So the effect of such adaptive learning rate is to make different entries update at different rates. If some entries grows fast, this entry will also grow fast. So the denominator will also be large. So by division, such a growth can be balanced. If some components are small, then n the corresponding component in n is also small. So by division, its updating rate will also increase. So will somehow balance the rate of update. The other is to use the moving average. You can see that this is a direct adding, right? But such an adding can cause the blow up of the variable. Yeah, you can blow up very quickly. So account for this issue, Hinton used the moving average. So by moving average, the largest and the smallest magnitude cannot go beyond the largest and the smallest value of G. So this removes the issue of blow up. So this is called the exponential moving average. The other example is using to modify the classical momentum method. This corresponds to the celebrated Adam algorithm. But you can see that this is the average exponential moving average. This is the adaptive learning rate. But Adam adds two more extra steps to account for the bias. This is the bias correction step. So we know that moving average and adaptive learning rate is crucial to adapt the traditional methods for deep learning training. So these are more a further summary. But we know that we have to use fast traditional algorithms for the deep learning training, right? There are two regimes of accelerated algorithms. The first is called heavy ball acceleration. This is invented by Polyak in 1964. It uses a momentum. This is called the momentum. By adding the current gradient to the previous momentum up to some scaling, the actual updated direction is given by m. This is the new direction of the momentum. The other paradigm is proposed by Nesterov in 1983. The major characteristic of this algorithm is that it does not compute the gradient at the current position theta k. Rather, it computes the gradient at an extrapolated point. So you can see that these two steps are exactly the same, but the point for computing the gradient are different. So actually, it's computing the updating direction in such a way. You move the point first and then compute the gradient here. Theoretically, Nesterov's method is better than Polyak's method. Yeah, it can be proven that for general convex algorithm problems, Nesterov methods can accelerate the gradient from k to -1 to k to -2. Yeah, but for Nesterov's algorithm, its acceleration can only be guaranteed in very special cases, such as the objective function has to be twice differentiable. So we can we want to apply Nesterov acceleration for deep learning training, right? We have seen that Nesterov's algorithm has been used because it corresponds to the momentum algorithm. So this is in the paradigm of Polyak. So we want to use the Nestrov's algorithm for another method for deep learning training. So this method is called adaptive Nestrov momentum algorithm. We call it ADAM for short. Yeah. So you can view it as the cousin of Adam. So by the two tricks of adapting the traditional algorithm for deep learning training, we also want to apply the same tricks to Nestrov momentum. But the first step gave us an obstacle because the current deep learning platform does not support the computational gradient at another point. You have to propagate once more in order to compute this gradient. So it will waste a lot of memory. I will say in the next paper that this gradient computation is very memory consuming. So if you propagate twice, then you will double the memory consumption. So it's definitely not good for the large model training. So we have to avoid this step.
Also double the computation time?
Yes, both memory and computation time will double. Yeah. So we want to remove this step by the idea is by the Taylor expansion, right? So the gradient here, we want to expand this value at theta k. So the first order expansion gives us this approximation. Then we replace this term using the third relationship. It gives this theta k minus theta k minus 1. So this further gives us an approximation. It becomes the difference in the gradient. So we can still compute the gradient at the current point, but the momentum added the number, the increment in the momentum is given by the new value of the gradient. But it's very interesting that although this step is only heuristic, we can rigorously prove that this reformulation is exactly equivalent by some variable substitution. We can prove it. They are exactly the same. Yeah. So by this reformulation, we avoid the extrapolation, and this reformulation is more consistent with the current deep learning platform. And we can see that this gradient difference has some information in the second order, because the gradient difference is this. So it accounts for the sum of the second order information. So this can explain why our method can be faster. Yeah. So we can apply the two tricks. The first is the exponential moving average. So you can see this is the new gradient, right? So we can use the moving average to compute the first order momentum. And we can also use this moving average to compute the second order momentum. Then this is the adaptive learning rate. Yeah. But further, we can do some engineering handling. First, we separate the moving average of the gradient difference and the moving average of the gradient itself, because they are of different physical meaning. So we can separate them. And we can further break the coupling between the gradient difference and the gradient itself by introducing an independent variable, beta 2, to replace beta 1. In the first situation, all the beta are the same, but for the second situation, the beta 2 can be different from beta 1. So this finally gives us the ADAM algorithm based on this reformulation, we can have this pseudocode. The first is to compute the moving average of the gradient difference. The second step is to compute the moving average of the gradient itself, and then add them together. Then we can compute the moving average of the second momentum. And then this is the adaptive learning rate. But here we add one more coefficient here to make it, this is called the weight decay. Weight decay is very important for the transformer, the training of the transformer. If there's no weight decay, this is typically for the training of convolutional networks. But for transformer with better at the weight decay, that will make the training much more stable. But people familiar with the optimization, they can ask, they may ask what's, because the Nesterov method has been used in deep learning training, such as the Nesterov accelerated gradient. Yes, it has been used for training of deep networks. It's formulated like this. So we can see that for the vanilla NAG, it still computes the gradient at an extrapolated point, and it still uses the scalar step size. It does not use the adaptive learning rate. So this explains why it does not perform well and is not used anymore in nowadays. The other algorithm is called NADM. It's the computation of the combination of Nesterov acceleration with the ADAM. So it's called a NADM. Its final formulation is like this. It still have the moving average of the second moment. This is also moving average of the first moment, but after correction, and that means it's divided by this scalar correction. But we can see that it does not involve the gradient difference here. It only uses the gradient itself. Then why? How come? Because this is the equivalent form of the NAG, but for avoiding the computation of the gradient at an extrapolated point, the author simply approximated by the gradient here and added the momentum in the variable directly here. We can show that these two algorithms are not exactly equivalent. Although empirically, you may think that they are equivalent, right? You can add the momentum in the variable into here, because in the next step, this will become the variable here, right? It's at a different time you use the momentum, but because it does not consider the algorithm very carefully, these two algorithms are not exactly the same. So the gradient difference does not appear in the end. So as I said, the gradient difference has some information for the second order. So that may explain why NADM nowadays is not used very frequently anymore. So for the new ADAM algorithm, we will show you that it has good generalization ability to various architectures that's very frequently used in the community. It achieves SOTA results for all the architectures if you run the same number of epochs. On the other hand, if you just stop at the same accuracy, then we can you only need 1/2 or 2/3 of the number of epochs, saying that it can save, it can be 1.5 or twice faster than the traditional algorithms. And it's more robust to best size choice. Best size also affects the accuracy. But if an algorithm is very sensitive to the batch size, you have to try different batch sizes in order to pick out the best one, right? So it will add to the difficulty of the training process. But if an algorithm is robust, is almost constant for different batch sizes, that will make the training much easier. And the fourth is very important, that we can prove that our algorithms matches the best known lower bound, theoretically lower bound.
So I have a question. So about good generalization. So do they go to different solutions, or do they go to the same direction, same solution, but your method is faster to go there?
No, it's not definitely not the same solution, because the accuracy is not the same. So, but we compete with the optimal optimizer for different architectures. So, for example, for CNN, usually Adam is the best, and for VIT, Adam W is the best.
Yeah, let's fix one model. Then you have several different optimization algorithms.
Yeah.
Then, okay, I'm sure yours is the fastest.
Yes.
Then you say also the generalization performance is the best. So does it mean that your algorithm goes to different solutions than other optimization algorithms? Or they are all going to the same solution, but because yours is faster, that's why you have better test.
Oh, yeah. The solutions are definitely different. Different. Yeah.
So then still we need a kind of understanding why your method can achieve better generalization performance.
Generalization is a mystery, actually. For optimization, they usually don't prove that we have better generalization, but this can only be validated by experiments. So there's still some parameter tuning in the process, but it's definitely much easier than the traditional methods. Yeah. You have to tune much less, and we can also provide the guidance for you to the training. So, say the Kaiming also write a technical report to tell you how to train the CNNs better. Yeah.
I think somehow if all the optimizers choose the same correct solution, then maybe we need to carefully consider the transition, right? But if only this algorithm choose the correct direction, all others choose similar but somehow deviated direction, then maybe it's intuitively easy to understand why the solution chosen by this algorithm can generalize better.
Yeah. Generalization is never proven in the for the optimization algorithm, because we don't know how to relate these two regime together.
Okay, I have a follow-up question on the parameter. I think the method introduced additional parameter to incorporate the difference of gradients. Do you have some guidance for tuning that?
Yeah.
Beta 1 and beta 2?
Yeah, beta 1, beta 2, beta 3.
But we can we have some empirical rule to fix the ratio between beta 1 and beta 2.
So for the theory, I think you maybe should to specify the beta to achieve the bound.
Oh yeah, we can give you some in my paper we give you some choice of the beta 1, beta 2, but that's only in the order.
Okay.
We still have some constant that's dependent on the process.
So I'm interested in the theory in accordance with real implementation, or you need to, for example, use some other guideline to tune the.
We still need some guideline, because in theory we only have O here. Such as beta 1 becomes O something. So O is still constant. Yes. So
sorry, I have a question like that. Sorry, maybe the next page. Yeah. So currently So I have an observation that in the image classification problem, we usually use some SGD with moment optimizer, and in RL we usually use Adam.
Yes.
Yeah, because in RL the variance is very big.
Yeah.
So I want to ask if the Adam here has some tricks or more better trade-off between variance and bias during the optimization, because you make use the RL.
I will show you, but for the very details of training, I don't get it. Yeah, but it's not very difficult because my student is very weak in engineering. Yeah. If some people from OpenAI or DeepMind, I think they can tune much better.
Thank you.
So this is the theoretical result. We know that for Lipschitz gradient, if the objective function is Lipschitz, has a Lipschitz continuous gradient, then the low bound has to be at the same level of epsilon to -4. Epsilon means the accuracy that you want to have. That means the gradient, the magnitude of the gradient. So you can stop at the different stationary points. Yeah. At the station point, the gradient becomes 0. Yeah. So we can see that although for epsilon, all these methods have reached the epsilon to -4, but their other factors are quite different. Some have D here. D is the dimension of the problem. For example, for ChatGPT 3.5, right? He has 175 billion variables. That means D equals to 175 billion. So it's a huge number. So in theory, our method should be better than those including D here. The only other method, add a belief, which does not have D here, we can compare is coefficient. Our coefficient is smaller than it. But constant is not a big issue, right? But in reality, we have known that add a belief has been outperformed by Adam W. So in theory, in the experiments, we only compare with the Adam and Adam W here. And if the objective function is has Lipschitz continuous Hessian, it is known that the complexity lower bound is epsilon to -3.5. So in this regard, we reached the lowest complexity, which is the same as the lower bound. Yeah.
So I think a big advantage is that your complexity is independent of dimensionality D.
Yeah.
And but it appears in previous semester. So I'm wondering what's the key step to avoid this?
I think because we don't assume the best side, because some of the algorithms, they have to assume the best side. So the best sides, they have to depend on D and epsilon. But in our proof, we don't have to make such an assumption.
This difference is huge.
Yeah,
yes.
For a large model.
Yes, it's huge. Yeah. So we can look at the experiments. We have done a lot of experiments. It cost Zhouchen Yang, Professor Zhouchen Yang, when he was in the CAI lab. Yeah. So he told me the experiments cost him $1 million. So the first is on CNN. We tested 4 kinds of convolutional networks without tuning architecture and data augmentation. We just replace the training algorithms and keep all the other factors the same. You can see that for the same number of epochs, we all reached the same, the highest accuracy. Yeah. And for this is for to compare all the existing training algorithms. Yeah, we also achieve the best accuracy. Then we can, if we just want the same level of accuracy, yeah, we can see that it saves 1/3 number of epochs. The other is on VIT. We can see the same phenomenon. We all outperform Adam W. Yeah. And when we want the same number of accuracy, yeah, we only need half of the epochs. This is the test on the robustness to batch size. Yeah, for lamb, yeah, which is designed for large batch size, but it still has 1.4% of variance of difference when the batch size changes from 1K to 32K, while our method only has 0.9 difference. One more VIT, yeah, we can test on MAE, VIT. We all perform better than Adam W. And this is for mask CNN and deter on the object detection and instance segmentation tasks. Yeah, we also achieve higher accuracy. This is for the diffusion model. Yeah, it's obvious our reconstruction quality is much better. This is for reinforcement learning. Yeah, the green line is obtained by our by a dam, but the blue line is for Adam. Yeah, so we can see the big difference between them, especially for this example. I don't think it can catch up. This is for the LSTM and the transformer SL. We also has the best performance. And for different training steps, yeah, we also have lower capacity. And test on ChatGPT-2. It was a big model 3 years ago, yeah, but nowadays it's relatively small. Yeah, we have smaller parts at K and BERT. Yeah, we consistently outperform. So now goes to the second. Any questions for this work?
Yeah, I'll ask some questions. In the beginning, I thought this work is extremely theoretical.
Mm-hmm.
But in the end, I found you have a lot of experiments.
Yes.
Mm-hmm.
So, are you intended to do so originally, or the reviewers require you to do so?
No. At the beginning, we have written yes, we have written all of these experiments. So the review is very quick. After the first round of review is already minor revision.
Okay. Yeah, because maybe the paper is very strong.
Actually, it has been used for real large language model training in Sky work because the Zhouchen Yan is also the chief scientist of some big companies. He applied the method to train the big models.
And also, when you introduce the Nestrov trick, you have two equations where it is approximately equals to something.
Mm-hmm.
But you claim that in the end, the two
Yeah.
duration algorithms are exactly equivalent. I didn't follow that part. Can you?
Actually, yes.
Yeah,
there's some half page proof
I see.
to show this. Yeah.
Okay, I see. Thank you.
So actually, I'm asking students to do different reformulations and then combine with the moving average and adaptive learning rate to find out which is better.
I see. So have you used the large language model to help you prove this?
Oh, actually, I did one. No, it's not yet exactly. I actually done a work to search. You use the reinforcement learning methods to search for the training algorithm. It actually returned one good algorithm. Yeah, so
Okay.
we are publishing that algorithm.
Okay, thank you.
With the new reformulation, can you somehow obtain a new interpretation of Nestor observation algorithm?
Oh no. This reformulation. I can only say that the gradient difference. The only thing I can say is the gradient difference gives information of the second order. Yeah. Nesterov's acceleration trick. No one understands.
Yeah, it's somewhat mysterious.
Yeah. It shows you by proof that you can accelerate, but on the intuition, no one can explain well.
I have a question. So currently, do you think it is a paradox between the generalization and the convergence? Because so it's followed my previous question, because I think maybe it's in the classification problem we use SGD because it can converge very fast. But in the RAO we hope it to be stable. Although it cannot converge to some global points, we do not care. Even in the current RAHF, the amount of data and the parameter is very large. So we want it to converge very faster, at least to somewhere instead of to the optimal point. So I think maybe there are paradox between these two metrics too. So how do you think?
I think when you want to reach a more stable point, you can add the sharpness awareness regularizer into the objective function, then still use the traditional algorithm to train it. Sharpness awareness regularizer.
So it's about the loss, right? Instead of the optimizer.
No, it's about the formulation.
The formulation. I see.
But actually, they are somewhat equivalent, because if you add a regularizer after derivative, after differentiation, you can have an actual gradient for the regularizer. You can add it to the optimization algorithm. Then you can say that this actual term is some correction term in the optimization algorithm.
Yes.
So it's actually equivalent.
I see. Thank you.
Now comes the second work. We know that memory is actually very important when in training. Say if all the clusters can compute batch size 16, but you want to work with the batch size 64, then you have to divide the work to 4 clusters, right? So in order to account for this issue, there has been many work in order to parallelize the process in order so that the parallelism is more efficient. And then still the communication has to be reduced. Otherwise, you cannot save your time. This is the typical training loop. I believe that most of you have been very familiar. Yeah. So first, we do the forward pass to compute the values, or call the activation at every node of the network. Then you compute the gradients by the backward pass. If this the gradient at this node has not been computed, the activation at this node has to be stored. Otherwise, you cannot compute the gradient. So you have to compute this gradient first, and then release the memory for the activation here. Then you use the optimizer to update the values at the nodes. So this is we can summarize the training step basically in 3 steps. Then we can look into the memory use on the 3 steps. After some initialization for the forward pass, because more activation values has to be stored, then the memory consumption increases. Yeah. And then this is the backward pass. The memory for the gradient reduces because the more nodes, the memory for the activation can be released, but the memory for the gradient has to increase. So we can see the blue path increases, but the red path decreases. And for the third step, when this comes in the optimizer, say Adam W or something, you can have to introduce some intermediate variables. So you can see there's a peak here, yeah, right? This accounts for the intermediate variables. Then you repeat this process for different epochs. So actually, if we want to develop a training system, we have to control the peak memory, the maximum number of the memories that you use, not just the average memory, because when you apply for these intermediate variables, you have to extra requirement of the memory.
What happens? So before step 1 starts, so you have a gray box.
Oh, that's also a black box to me. It's just by tested by the software. Yeah, so we have this figure. Mm. So this is drawn by the software, not manually. Not manually.
Even if you cut the peak in the latter stage, but as far as you have a big gray box, yes, the improvement it does not really work.
Oh yeah, but I think the engineers may help us to cut this part. Okay, that's a very good question. So people actually has done a lot of work to cut the peak memory. Actually, the most celebrated trick, and everyone can think of, is called the gradient activation checkpoint. That means we don't have to store the activation for every node. We store the activation value for every several layers. Then for intermediate layers, when we want to its activation, we compute from the nearest layer that has the activation values, then do the forward propagation once more. This is a typical trick to use the computation for the storage, right? 以时间换空间哈，use the time for the storage. So we can look into the working process of some for atom W. Say we can see that for these two steps, we still have to keep GT here because GT is used to update MT, is also used to update VT. But after this step, we think we can see that the GT is no longer used, right? MT is now corrected to have MT head, VT is corrected for VT head. So now that the GT is no longer used, we can use GT to save this part, right? We can, but we cannot use GT to save both, right? At least we can use GT to save this part, VT here, VT head here. So this reminds us we can reutilize the gradient, the memory for the GT after some steps of the training algorithm to store other intermediate variables. We can show you that this is doable for most of the algorithms. Yeah. So our algorithm has 3 steps. The first is to reformulate the algorithm if necessary and applicable. So you have to examine the algorithm. If the current form of algorithm has no, if the update of GT is at the end, then you cannot reutilize it, right? And so you have to update the GT at the very beginning, as early as possible, and you use the and make the update on the intermediate variables as late as possible. Yeah, so then you can reutilize the memory for the gradient. That's the basic idea. Then you can use the oldest memory space, say GT minus capital T, because for different algorithms they save different number of gradients. For atom, you only save 1 gradient. But for a DAN that I just introduced, we save 2 gradients. Then you can move the memory to account for the latest gradient information. We can show you some examples of some optimizers of good performance, so that you can use in the future. Say for the atom W, after the reutilization of the gradient memory, we appended with the R here. So as I said, we can use GT to save M hat here. So we can save 1 vector. But for this algorithm, we don't have to reformulate it because we can already reutilize the gradient memory. So move is done for every algorithm, so we don't explicitly show it. So for atom W, memory consumption is reduced from 5 vectors to 4 vectors. So theoretically, it has 20% memory saving in the optimization step. And these 2 algorithms are exactly the same, actually, because it only reutilizes the gradient memory. So we can see that for atom W, for typical training of big model, 1.8 billion the extra intermediate variables were cut by one. So it saves us 8 gigabytes. I think it's a big, large amount because for typical GPU, one card has only 80 gigabytes, right? So you can save 8 gigabytes. For then algorithm that I just introduced in the first part of this talk, we can examine it. So we can see that we can use GT-1 to compute VT, to save VT here. And we'll further, after updating NT, we further use GT-1 to account for the square root of NT. So it also saves one vector. So theoretically it has seventh memory saving during the optimization phase. For the Lion algorithm, is actually searched. It's proposed by DeepMind. I think they use the reinforcement. Actually, not reinforcement learning. They use genetic algorithm to search such an algorithm, and it is shown has good performance. And since it only updated by the sign of the gradient, it has very good memory communication saving. But for this algorithm, it has only 4 lines, 4 or 5 lines. So as its original formulation, we cannot apply the gradient reutilization technique because the GT is always used. But for the left part, this is the original formulation. So we can see that MT-1 has to be saved even if it has been updated to MT, right? Because in the update of CT, we still use MT-1. So it's very easy to reformulate it, right? We substitute the MT-1 by MT minus 1 minus beta 2 GT divided by beta 2, right? Then substitute this into the second equation. Then we reformulate the original line by this. Then by this reformulation, we are able to reutilize the gradient G to compute MT instead. Then the rest part of line is the same. So by this algorithm, by this trick, we can save 1/4 of the number of the intermediate vectors. So I show you the experimental results on really large models. You can see this is very relatively small, but we can compute up to 13 billion number of variables here. So it's a relatively large model. So these are the different large models that we have tested. We also utilize the zero technique to align with the industry practices. So for different models of different sizes, we all achieve different levels of savings. Some is large, such as more than 20%. Some is small. So it's dependent on the setting of the system. These are more experiments on ADAM, memory reduced ADAM. We can see that it has nearly 15% memory saving, but some are small, only less than 1%. So this is for the Lion algorithm. We can achieve 25 savings. It's very easy to use this trick. You can incorporate our code in your training process. I provided the barcode here. This QR code here. So in conclusion, the training of large models, you should not consider the speed of convergence only. You have to also consider the peak memory too. So we have some primary results on both directions and tested on real situations. So these are the QR codes for the both algorithms. You can save it for your use. For then, it has been the paper published last year has nearly 300 Google citations. And it has been used for many deep learning and large model projects, such as Hugging Face, OpenML, NeMo, NVIDIA NeMo, etc. So these are the books, Chinese and English books I published in the past 4 years. Maybe you are interested in it, in that. Then I'm happy to take the questions.
Okay, thank you very much. So let's start from the question by Shuo in the chat window. So thank you for the great talk. So this is Zhouchen from our team. And may I know that can we have any new metrics to better, more reasonably measure the convergence behaviors of our stochastic optimization algorithm in the current large models? I ask this because I think the convergence targets would be different in large models from the traditional models.
Oh, yes, yeah. That's from an engineering point of view. For the engineering point, maybe you are more concerned on the number of breakdowns during the training process. Yeah, when the training breaks down, you have to manually fix and restart the training process. Currently, I don't in the research community. I don't think there's a new metric to measure the training process. They only care about the test accuracy and the number of epochs. Even also the number of tokens that you can achieve some level of accuracy. Yeah, but they are relatively equivalent to the number of epochs.
So I think the test accuracy is somewhat difficult to think about.
The test accuracy is still in the lab, not in the real situation.
So like if it's a foundation model, it's a pre-trained model, then we don't really have downstream tasks when we train the foundation model. Then we can't really measure the test performance in practice.
Oh yeah. So for large models, yeah, I think they have some empirical rule. When you look at the training process, they somehow can predict the performance on the for the given task. Yeah, they have some empirical rule.
Other questions?
And they very often they just compare with the Adam, which is the benchmark.
Yeah.
If you can converge faster than Adam, and then maybe you can.
When we write a paper, this is fine. But if it's a real training, we don't have Adam anymore. We just have one trial.
But in real training, they do run first with
Oh yeah.
Yeah.
I see.
Okay.
Yes, of course.
So currently, I think there are many methods. They considering the memory complexity. They use low rank methods to compress the optimization states. Do you have any comments on this class of methods?
Oh yeah, but that does not affect the convergence speed. Yeah, it can still be combined with the gradient utilization algorithm, because our method simply saves the whole vector. But for the low rank methods to compress these variables, they can still be incorporated.
Yes, so it can be somehow combined.
Yeah, definitely.
Thanks.
If there's no further questions, so let's conclude the seminar. So thank you very much again.
Thank you, everyone.